So in our last video, we began the process of convincing ourselves that what linear algebra is about is vectors, and what vectors are about is linear combination. Linear combination is the operation that powers linear algebra because it defines what vectors are permitted to do. And so in our last video, we took a couple of examples of vectors just in the xy plane and looked at what linear combination looks like, both from an algebraic perspective and also from a graphical perspective. So if I have two vectors v1 and v2 sketched here, that the linear combinations are the results that I can get by multiplying those vectors by scalars and adding those results together. So any of the vectors in purple here are some linear combination of the v1 and the v2 that I have. So in this video, we want to kind of ask the opposite question. If I have a target I'm trying to hit, let's say the vector negative 2, 8, how do I find out whether that vector, that negative 2, 8, is some linear combination of v1 and v2? How do I solve that vector equation to discover whether there are some weights whose linear combination define negative 2, 8 as a linear combination of negative 2, 1 and 3, 2? So is this B some linear combination of this v1 and this v2? That's the question that's going to get us back to our roots, in a way, of thinking about equations. So from a graphical perspective, if I want to know whether negative 2, 8 is some linear combination of negative 2, 1 and 3, 2, what I could do is draw the point negative 2, 8 here in the xy plane, draw my two vectors, negative 2, 1 and 3, 2, here in the plane as well, and then just take a bunch of different linear combinations and see if I can get one of them to exactly equal negative 2, 8. So let's see, v1 looks like it can take me in a northwesterly direction, so I'm going to add more and more of that into my recipe until I can get kind of close over there. And then v2 can kind of take me in a northeasterly direction, or if I decrease the amount and go negative, it can take me in a southwesterly direction. So if I dial that in just right, I find out that yes, I can in fact make negative 2, 8 out of a linear combination of negative 2, 1 and 3, 2. All I have to do is add in 4 copies of v1, so v1 stretched out by a factor of 4, and 2 copies of v2, v2 stretched out by a factor of 2, and when I add those vectors together, 4v1 plus 2v2, I indeed get negative 2, 8. So from the graphical picture, it's evidently very possible to make negative 2, 8 out of a linear combination of negative 2, 1 and 3, 2. The weights that I need in order to make that happen are respectively 4 of my first vector and 2 of my second vector. So evidently, the answer is yes, that's possible to make a linear combination of v1 and v2 equal to this b. We just need the weights to be 4 and 2, respectively. Namely, 4v1 plus 2v2 is equal to b. But how would we have found that out without using my nifty little app, right? Without having a graph in front of me that I can manipulate? Well, clearly the answer is algebra, as it usually is. Right? How can I solve for those weights, x and y, if those x and y's are unknown? Well, take a look at what this linear combination of v1 and v2 with the unknown weights x and y, let's take a look at what that looks like if we actually simplify out the algebra. X times the first vector plus y times the second vector is going to give me, after I do the multiplication here, negative 2x plus 3y in the first component, 1x plus 2y in the second component, and on the right side of the equation, negative 2 and 8. Namely, we get exactly a linear system of equations of the type that we already know how to solve, based on what we've already done in the course. So the question of what are these unknown weights that make a linear combination of v1 and v2 equal to b is exactly the question, what unknown variables x and y solve this linear system of equations. And when we put that linear system into its augmented matrix form, a couple things should pop out at us. First of all, the right-hand side in my augmented matrix is exactly the vector b that I'm trying to reach in my linear combination. Meanwhile, the coefficient matrix on the left side of my augment bar in my augmented matrix has as its columns negative 2, 1 and 3, 2, the vectors v1 and v2. So that linear system, whose solution answers the question, what linear combination of v1 and v2 gives me b, has as its augmented matrix a matrix whose columns are v1, v2, and b. That's pretty convenient. Now we're beginning to get an understanding of why linear combination is so central to what we're studying. because linear combination is exactly the operation which defines a linear system of equations in the first place. The first column of this augmented matrix is V1. The second column is V2. The third column is B. So that means that augmented matrices and the solutions of linear systems of equations that we know how to find have the power to answer questions about linear combination. What linear combination of V1 and V2 gives me B? And the unknown weights are the x's and the y's, the unknowns in my system that are lurking in the background in augmented matrix form, but in equation form, they pop right out here at us. Right? So a lot of what you'll do in this whole chapter is thinking about how to translate questions about vectors into questions about systems of equations, and then retransform the solutions that we get from those systems back into what they tell us about the vectors that originated those systems in the first place. So this is really about using the tools of linear algebra to solve for those unknown weights, and those unknown weights define a linear combination for me. Indeed, if we do the elementary row operations and we row reduce this matrix as far as possible, we do end up with the row reduced echelon form being 1, 0, 0, 1 in the coefficient matrix and 4, 2 on the right hand side, which when we translate it back into equation form is just x equals 4, y equals 2. In other words, that's how we could have discovered the weights that make a linear combination of this V1 and V2 equal to this B, and therefore the weights which make a linear combination of this V1 and this V2 equal to this B. The 4 V1s that I needed to put into my mixture, the 2 V2s that I needed to put into my mixture, such that when I add those together, I get the result that I was looking for. And one final comment before we wrap up this video. Once we have set down a couple of vectors, in this case, -2, 1, and 3, 2, right? And we think about what the linear combinations of those vectors can do, what it actually does for us in this picture is it defines for us a new kind of graph paper, in a way. Right? That if I lay down on top of my xy plane here a grid that includes all of the integer multiples and integer linear combinations of V1 and V2, then what I get is kind of a skew graph paper, in a sense, this green grid. And by starting from the origin and counting along my grid, I can sort of count a new system of coordinates. That if I go out to one copy of V1, I can think of this as the point 1, 0. So the V1 is standing in as my new x-axis, if you like. 2 copies of V1 would put me there, 3 copies of V1 would put me there, and so forth. Meanwhile, V2 can be my new y-axis. 1 copy of V2 is going to put me here, so this is 0, 1, 0, 2, 0, 3. And when I start adding those together and not just multiplying, I can get to points like 1, 1, which would be right here, 1, 2, which would be right there, and so on. So as soon as I have 2 vectors in my xy plane, even if they're not along the xy axes themselves, they can define for me new x and y axes. And I can use that new graph paper that I get defined by my new axes to give me a new coordinate system on the xy plane. And the point -2, 8 is right here. It turns out to be one of our points that's actually on my graph paper. It's on my graph paper because how can I get to this point -2, 8 using my green graph paper lines? Well, I just need to start from the origin and go 4 steps in the new x direction, 1, 2, 3, 4, and then 2 steps in my new y direction, 1, 2. And I get to the point which I used to call -2, 8. But on my green graph paper, I can give it the coordinates 4, 2. If you grasp that example, you're going to go a long way in this chapter, because really, over the next 2/3 of a semester, we're going to be building all of the tools that are necessary to think about how to use linear algebra to define new coordinate systems and coordinate transformations. And that's a big part of what you can use linear algebra to do very powerfully in applications. Defining linear combinations defines for us a new way of measuring coordinates. And that's super important, super useful, and you can get a long way into our story of linear algebra if you really understand what that's about.